The topic is Newton-Gregory's forward and backward interpolation formula. So here we will consider equispaced arguments. So suppose we have a function fx which is known for total n plus 1 equispaced arguments, that is x0, x1, x2 dot dot xn, and their corresponding value y0, y1 dot dot yn is given, and all these arguments are equispaced. That means xr, where r runs from 0 to n, xr will be equals to x0 plus rh. That means the distance between any two consecutive arguments are h. h equals xr minus 1. That one. Okay, this is called the length of each space. And all that values are given. F of y0 equals f of x0, y1 equals f of x1, and yn equals f of xn, and so on. Now if this is given, then we have to find out the interpolation formula for the function fx. That means our object here is to find a polynomial px which degree is less or equal to n, and which is much simplified form, and which can agree with fx on that n plus 1 set of arguments. That means p of xi equals should be f of xi, where I runs from 0 to 1 to dot dot n. Okay, so this finding this px polynomial is our main object here for that interpolating theory. So starting with, we are considering a polynomial px as a0 plus a1 into x minus x0 plus a2 into x minus x0 into x minus x1 plus a3 into x minus x0 into x minus x1 into x minus x2 plus dot dot an into x minus x0 into x minus x1 dot dot x minus xn minus 1. Okay, then obviously it's an nth degree polynomial, because from there we will get a term an into x to the power n plus some constant into x to the power n minus 1, and so on. So this is an n degree polynomial. We have to show that this polynomial is our required interpolating polynomial. That means this polynomial will agree with fx on that n plus 1 arguments x1, x0, x1, x2 dot dot xn. So starting with p of x0 is equals f of x0. Now if you put x0 over there, all the term will be cancelled out, only this one will remain there. So this equals a0, and f of x0 means also y0. Okay, next, so we got the value of the first constant a0, which is equals f of x0 or y0. Keep it as number 1. Next, putting x equals x1. So if you put over this px, x equals x1, then this and all the remaining terms will become 0. Only the non-zero term will be this and this. So it will become a0 plus a1 into x1 minus x0. We are trying to get the value of a1. So a1 will be p of x1, that means f of x1 minus a0. a0 is f of x0 by x1 minus x0, right? Now if x1 minus f of x0, that means forward delta operator f of x0 by x1 minus x0, that means h. So this is equation number 2. There we got the value of second constant a1 equals this. So first constant was f of x0, second constant is delta f of x0 by h. So in the similar manner, a2 will be delta square f of x0 by h square. Then a3 will be delta cube f of x0, sorry, that one will be factorial 2 into h square. a3 will be delta cube into f of x0 by factorial 3 into h cube, and so on. So in the similar manner, an will be delta to the power n f of x0 by factorial n into h to the power n. So we got all the value of the unknown constants a0, a1, a2 dot dot an. Now we are going to put that over px. So the interpolating polynomial px will become, first is a0 means y0 plus x minus x0 into a1. a1 is delta y0 by h plus x minus x0 into x minus x1 into a2. a2 was delta square y0 by factorial 2 into h square plus dot dot the nth term, that is x minus x0 into x minus x1 dot dot x minus xn minus 1 into an, that means delta to the power n y0 by factorial n h to the power n. Okay, now this is our interpolating polynomial, that means that fx is equivalent with this px. Now let us choose u equals x minus x0 by h. Then wherever we get x minus x0 by h in that formula over px, we are going to replace it by u. So for the first term there will be no u, as there is no x minus x0 by h. For the second term, for that part x minus x0 by h, we can put u. Next for that one, and taking one h from there, we can put u. Okay, now again u equals x minus x0 by h. So from there we can write x equals x0 plus hu, and again we have xr equals x0 plus rh. Right, we already got this because we are dealing with the equispaced arguments. xr equals x0 plus rh, where r runs from 1 to dot dot n. So x minus xr, because we got so many terms in px as x minus x1, x minus x2 and so on, so we need x minus xr. There is x minus xr. From this line we get that it becomes u minus r into h. So x minus x1 will be u minus 1 into h, then x minus x2 will be u minus 2 into h, and so on. That means from there x minus x1 by h will be u minus 1, from there x minus x2 by h will be u minus 2, and so on. Now putting all that values of x minus x1 by h, x minus x2 by h and so on the value of px. So then px will become y0 plus u into delta y0 plus u into u minus 1 by factorial 2 into delta square y0 plus u into u minus 1 into u minus 2 by factorial 3 into delta cube y0 dot dot plus u into u minus 1 into u minus 2 dot dot u minus n minus 1 divided by factorial n into delta to the power n y0. This is the required interpolating polynomial. Okay, now this is called Newton-Gregory's forward interpolation formula. Now when we will use that forward interpolation formula, when we are trying to find the value of fx where that x lies near the argument x0, where that x lies near the argument x0, that means it is near the top of the table, near the top of the table, then we will use that forward rule. Now again we have another rule which is called backward rule. We will use that rule when the argument x lies near the argument xn, that means near the bottom of the table. Okay, so this is the rule for the forward interpolation formula. Now let's check the rule for backward interpolating formula. Exactly the same, only these things will become changed. So next one is backward formula. this is fx, which is equivalent to, let's name it by pb. P means this polynomial, b for backward. So pbx, this will be equal to yn plus u into delta yn minus 1 plus u into u plus 1 by factorial 2 into delta square yn minus 2 plus u into u plus 1 into u plus 2 by factorial 3 into delta cube yn minus 2 plus dot dot u into u plus 1 into u plus 2 dot dot u plus n minus 1 by factorial n into delta to the power n y0. This one, this is called the backward rule. Exactly, just by applying same procedure we can get this one, where that u is equals to x minus xn by h. Here we are choosing xn, that means the last argument given. So u equals x minus xn by h. This formula is called Newton-Gregory's backward interpolating formula. And when will we use this formula? When we need to find out the value of fx, where x, that argument, lies near the end of the table. Near the end of the table. That means near xn. That is near the last argument of the table. Then we will use that backward interpolating formula. Okay. So we got two formulas, forward formula and backward formula. Forward formula is used when we are trying to get the value of fx where the argument x lies near the top of the table, that is near x0, and backward when this x lies near the end of the table, that is near xn. Okay, so whenever the question will be given to us, we need to understand that which formula do we have to use to get the value of fx. Okay. So starting with an example, compute number 1 f of 0.5 and number 2 f of 2.8. Compute f of 0.5 and f of 2.8 from the following table. From the following table, x and fx. X equals 0, 1, 2, 3, equispaced arguments. Then fx are 1, 2, 11, 34. Okay, this one. Now check 0.5, it lies near 0. That means this is our x0, so it is the starting of the table. So to get the value of f of 0.5, we need to use the forward formula. And f of 2.8, it lies near 3, that is the last argument, that is the end of the table. So to get f of 2.8, we need backward formula. So at first apply the forward formula to get the value of f of 0.5. Before that, we need the difference table. So to get the difference table, what we have to do? We only have to make this column x, then fx, that is y, then delta square y, delta cube y. Write down all the values of x: 0, 1, 2, 3, and then 1, 2, 11, 34. Okay, now you know how to calculate delta y. Just this one minus this one and write it in the middle of the line. So 2 minus 1, 1, then 11 minus 2, that is 9, then 34 minus 11, that is 23. Next is delta square. For 9, this is 9 minus 1, that is 8, 23 minus 9, that is 14, then delta cube y, that is 14 minus 8, which is equals to 6. Okay, so now our x0 is equals to 0. Okay, so we are trying to get the value of x equals 0.5. So we need the value for y0, delta y0, delta square y0, delta cube y0, and so on according to the rule. So this and this will be the value we need there. This is delta y0. First one is y0 1, then delta y0 1, delta square y0 8, delta cube y0 6. Okay, so we will use that. At first, writing down the formula. The formula is forward formula fx or px equals y0 plus u into delta y0 plus u into u minus 1 by factorial 2 into delta square y0 plus u into u minus 1 into u minus 2 by factorial 3 into delta cube y0 plus and so on. Now check, there is no other term after delta cube y0. That means all the other terms will become 0, so no need to write them. So this is our required formula. At first we need to get the value of u. So u was x minus x0 by h. What is x? X is that argument on which we need to find the value of fx. So x is here 0.5 minus x0, that is the initial argument which was 0. Then h means the length between each argument, that is 0 minus 1, which is equals 1. So it will become 0.5. Now we all know all the values. We already got the value from the table, that is the values of y0, delta y0, delta square and delta cube y0. Now put all these values. So the value of f of 0.5, the given question, given argument, f of 0.5 will be equal to, at first is y0, which is equals 1 plus u, that is 0.5 into delta y0, this is again 1 plus u, this 0.5 into 0.5 minus 1 by factorial 2 into delta square y0. Delta square y0 got the value 8 plus u into u minus 1 into u minus 2 by factorial 3 into 6. Okay, so after calculation you will get the value of 0.875. So the value of f of 0.5 is 0.875. This is how we apply forward interpolation formula to get the value of fx where the argument x lies near the top of the table. Now moving to get the value of f of 2.8. Now 2.8 lies near 3, the last argument of the table. So to get this we will apply backward formula. Now for backward formula, let's write down the formula. Fx equals yn plus u into delta yn minus 1 plus u into u plus 1 by factorial 2 into delta square yn minus 2 plus u into u plus 1 into u plus 2 by factorial 3 into delta cube yn minus 3 and so on. And after that we don't have any other value, so I'm not writing it. Okay, so we need the value of u at first. U is x minus xn by h. X is that one what we have to find the value, that is 2.8 minus xn means the last argument given in the question, that is 3 divided by h, the space length, that is equals 1. So it will become 0.2. So the value of u is 0.2. Now we need the values of all this, yn, then delta yn minus 1, delta square yn minus 2 and delta cube yn minus 3. We can get this from our difference table. Now this is our difference table. This is our yn, right? Y equals fx, the last one. This is called yn. So this is our yn. Then this is delta yn minus 1. Then this is delta yn minus 2. Delta square yn minus 2. And then delta cube yn minus 3. So this and this. The last line, that will be our results. So we have to use these 4 values. So getting all that value, now I am putting it. So it will become yn was 34, then plus u, that is, sorry, that one will be minus 0.2, as it was 2.8 minus 3, so minus 0.2. So minus 0.2 into delta yn minus 1, that is 23, plus minus 0.2 into minus 0.2 plus 1 by factorial 2 into 14, next value, plus minus 0.2 into minus 0.2 plus 1 into minus 0.2 plus 2 by factorial 3 into 6, the next value. That's it. Now calculate this one. You will get the value as 27.992, which is approximate to 28. So this is the required value. 28 is the value of f of 2.8. Okay, this is how we use backward formula for interpolation.